But welcome everybody online here in the room. Appreciate it. And glad to see all of these wonderful faces that are here. I can't see you at home, but hi. And tonight is our December 2024 business meeting, which we only have 2 of each year. And that is great because tonight we need a quorum because we have some exciting things going on, which we will tell you all about. So let us get the party started, if so to speak. So here's your current board. Last time you'll see some of the smiling faces that are on some of these pictures that are up here. You've got outgoing me. You've got VP John is here. Outgoing Dave Faulkner is over there. And then we have Treasurer Matt here in the room. Outgoing Ahmed is helping check in people at home. And Jessie is also helping check in people. And she's in the room. So we have the full board here once again, which is great. So hi and bye. The elections, just a kind of a quick overview of how it's going to go on. Everybody in the room should have been signed in and received a ballot. If you have not gotten one, please go back up to the front because they missed you. And we'll have to tackle them later. Everybody gets 1 vote per family or subscription. If you have paid multiple times, doesn't count, you still get 1 for 2 years. So we have that. We have, we need 10% of the quorum, which right now is 75 people to be members logging in singularly to make our quorum. And at some point, the front desk will all say hi. And that tells me that we have got that. So that would be great. For the people online, you will be getting a poll / survey. I think that will pop up once we have quorum, and that will take you through the questions for the nominations along with the bylaws change that we are requesting. And I will have Mr. Zimmich come up here in just a minute, like in 2 minutes. Come on. And talk about that a little bit. So grab your microphone. Here we go. I'm going to put the next slide on to figure out what it's all about. And yeah.
Okay, the bylaws quorum requirement change. That's we proposed that the board did as a result of the past several elections, and pretty much every election that I really paid attention to, which is probably since I became a member of the board, so maybe 4 years ago. But it's been a challenge getting the quorum. And how close are we right now? Okay. This is actually looking very favorable tonight. Usually it's kind of a goat rodeo trying to get quorum. We have people calling people up and trying to get people to join the meeting so we have a quorum so we can have a vote. And what the reason for the bylaw change is we're growing at a phenomenal rate. We have, 745 members right now. And so that means we need 10%. So we need 75 people. So the quorum change is let's make that 50 or 75, whichever is less. And what we did is we looked in the bylaws and we saw another reference to that type of requirement. And that would be for members, a president can call a meeting anytime the president wants, a business meeting. Members also have the capability of calling a business meeting, but for members to call it, it needs 50 signatures or 10%, whichever is less. So that's what we used as the basis for this. And the only challenge or concern that I received regarding the quorum change, and it is legitimate, but unless you really think about it, but they said, well, the concern is, okay, so if we make it 50, then 50 members can run the club. Well, we have 700 members. If 700 members, if every one of those members wants to run the club, we would have 700 people here. That would be kind of crazy, but we would. And the thing is, the reality is that there's not that many people who really want to get into the business part of the club. And so let's make that 50 so that we're not jumping through hoops and end up having a business meeting like this where we don't have a quorum, so we can't take a vote. So now we have to have another business meeting the next month, and we have to month after month after month. So to alleviate that possibility, and if the members are concerned, then they're going to show up. And so that's the way I look at it anyway. So are there any questions about this quorum change? Okay. I'll kill time because Trina's busy. So we're ready. Okay.
Can you hear me?
Yep.
Okay, well, in the spirit of keeping business meetings fun, I think we promised Trina a skit for her last month as president. So this is our stab at that. I think we've talked about doing a skit going way back to when Clayton was president on his last night. We've never pulled it together. So here we go. Break a leg, everyone. Places. I don't think it's going, Trina. Okay. Thank you for calling the Minnesota Astronomical Society. Please hold. Thank you for calling the Minnesota Astronomical Society. Please hold. Thank you for calling the Minnesota Astronomical Society. How may I direct your call? Oh, all 110 Messier objects? Oh, congratulations. Oh, I heard it was windy out there on Saturday. Oh, your entire log sheet blew away? Oh, well, let me transfer you to the Metcalf Lost and Found. One moment. Thank you for holding. How may I direct your call? Oh, yes, Star Party at Yellow on Saturday, yes. No, Taylor Swift will not be there. No, no Oprah. No, I believe that Tom Cruise is probably on site somewhere filming a movie. But I believe Doug Neverman will be out there with the ELO committee. Okay, well, thank you for calling. Thank you for calling the Minnesota Astronomical Society. Please hold. Oh. Mr. President-elect, FedEx has just delivered your inaugural speech if you want to come out to the lobby and get it.
Thank you, Claire.
You're welcome. Thank you for holding. How may I direct your call? Oh, sure. The CGO 24/7 weather station information coming right up. Thank you for holding. How may I direct your call? Oh, the MAS store. Sure, we've got mugs, t-shirts, hoodies. No, I'm sorry. No grocery delivery. Thank you for calling. Oh, hello.
Hi there. I'm here for the MAS member at large.
Oh, the board member at large interview. Oh, of course. Oh, you must be Phil Ramsay. Oh, yep. Okay. Well, we're just going to have you fill out this application right there.
Thank you so much.
And you can grab a seat if you want to grab a seat right over there and let me know when you're done. Thank you for calling the Minnesota Astronomical Society. Please hold. Thank you for calling the Minnesota Astronomical Society. How may I direct your call? Oh, yes, the bylaws are coming out in paperback this month. Oh, yes, you can definitely pre-order copies. Oh, I think those would make wonderful stocking stuffers. Thank you for calling.
Look again. That's the pale blue dot. That's here. Oh, that's not. It's far better to grasp the universe that it is, really, than any persisting delusion. However satisfying it is.
That's very profound, President-elect. You have my vote. Thank you for holding. How may I direct your call? Oh, Astronomical League programs? Yes. No, I don't think we have one for UFO sightings, but if you want to recommend that to Jerry, let me transfer you right there. Thank you for calling the MAS. How may I direct your call? Oh, the budget? Oh, sure. Which line item? Oh, I'm not sure I know that line item. Oh, I don't know how much we spend on mousetraps every year, but let me transfer you to our treasurer. One moment.
The cosmos is within us. We are made of star stuff. Is this too corny? Should I go
Oh,
on?
I'm very moved, Mr. President-elect. I've never heard anything so profound in all my life. Like I said, you have my vote. Oh, were you done filling out that application? Oh, yes. All right. You may have a seat right here. All right. Well, before we move you forward in our job interview process, the board would like to ask you a few screening questions, or have me ask you a few screening questions. All right. Do you believe in UFOs, astral projection, mental telepathy, ESP, clairvoyance, spirit photography, telekinetic movement, full trance mediums, the Loch Ness Monster, or the theory of Atlantis?
No, I don't think I do.
Oh, all right. Okay, how about the JWST, astronomical conjunction, stellar evolution, the HST, cosmic microwave background radiation, Venus and Mercury transits, gravitational waves, gravitational lensing, supermassive black holes at the center of most galaxies, and the existence of exoplanets?
Oh, yeah, for sure.
Oh, all right. All right, I will get that information to our board, and I'm sure we'll be in touch. Thank you for coming in today.
Okay.
All right, thank you for calling the Minnesota Astronomical Society. How may I direct your call? Oh, yes, our next basic topic. One moment, let me double check. Oh, I think that Jesse Palmer is doing fashion tips for the observing field. Oh, thank you for calling. Oh. Oh dear, I think we've located our current president, Trina Johnson. She's no longer missing.
Oh, wait, are you the gatekeeper? Oh my God. I don't know.
Ms. President, may I get you a Pepsi?
Yes, but did you know Gozer the Traveler?
I think
There's
you should
so-
escort
so
her
many-
out to get her something to
Pepsi
drink.
might help. Fine.
Are you sure you want this job, Mr. President-elect? Thank you for calling the Minnesota Astronomical Society. How may I direct your call? You do? You have? You will? Why, certainly we can get a new member card to you in the mail right away. Thank you for calling. A new member! We got one! Everybody. All right, you can cut it.
Well, thank you very much, Claire. And as we are going forward with all of our announcements and such, until I get my headset back. So we have for President-elect, Valts Treibergs. Good job. Love the speech, love the speech. We have for Secretary, Miss Claire Weaverling. Yay. And you got the sites right. Perfect. And for the board member at large, Mr. Phil Ramsay. Yay. All right. And if anybody has any questions about or for the candidates, Send an email. We'll get back to you. All righty. And how are we doing through our little presentation here for quorum? Yay, we have it. Woohoo! Everybody give ourselves a round of applause. We got it. Perfect, perfect, perfect. Let me welcome the new members that we have coming in. Matt said we are at 749 total members, and that has stayed the same in the last 5 days from December 1st to tonight. So is anybody that's a new member in-house tonight that's up on the list? Okay, you must be all online. So everybody that's online that's a new member, please feel free to put in chat hi and welcome, and we'll say thank you for being here because we really appreciate it. So I don't see anybody there, but there we go. And then these, I'm sorry, it's a little small. I'm wondering, Noha, sir, we can cut my camera feed so we can see the entire screen. I'm sharing two screens right now, so go just do your thing. So these are the items between December and January, which we had to stop sharing for that, didn't we? No, it should be this one. All right, there we go. There we go. Now we can read that. We just needed the extra camera for the fun little skit. So we have a couple of meteor showers. We have the wonderful occultations and conjunctions and whatnot with Jupiter this month. That is going on, opposition going there. So that's wonderful. We have the Geminid, and of course we have winter solstice. So now we will start gaining sunlight, which is strange because it always seems darker in January when we're getting more. But that's all right. And then the Ursid meteor shower goes with the last quarter moon. And then January 2nd, we have the MAS monthly meeting. That's again online in person. But at that one, you get to have your new president, which we will announce hopefully before the end of the meeting here, but we'll just confirm it by Monday night, I think, is when we're going to do the official here. And we'll post it everywhere, Slack, emails happening, the whole 9 yards to make sure everybody is out there. In that case, let's, come on. I love it. I wish that, there we go. Okay, Loner Scope program. Anton, are you on tonight? He's not on yet. Oh, all right. Well, in the meantime, I know we don't have a camera. Oh, we don't have a camera in house, but oh well. You do that one? Is that one showing us?
Yeah.
Oh, perfect. Okay. Okay. No, that's fine. Everybody in the in-house can see us, so we're fine. The ones at home just. Oh. Oh, never mind.
Oh.
Then here, there you go. Smile, John.
People in the room don't need to see me on the camera, I guess, so you're just stuck with the real thing. Wow. The Loner Scope program, Anton, like I said, he told me he'll be joining late tonight, but I'll cover this. And now for any new members, I know there's none in the room, but for online, Loner Scope program is a very valuable resource for the club. We can check out scopes. We have 18 of them, and you just sign up and check it out. It's a first come, first served basis, and check it out for 30 days. I don't know the current status, but I know we have a good stock, and so you don't have to wait very long to get one. Solar scope would probably be something that you might have to wait for.
And how did they get there?
Yeah, and how you get it is right on our website. You can go to the Loner Scope request, fill out a form, and then Anton will get back to you. You tell him what type of scope you would like, and then he'll follow up. And we also have courses that are on DVD, and these are excellent. Highly recommend checking them out. It's one of our resources that is not used very often. And if you do check these out, if no one else is waiting in the pool to check it, if it takes you more than 30 days to get through, you can extend another 30 days until I'll have no problem with that.
All right, do we have everybody's ballots that are in-house here?
You don't have
Everybody's, oh.
Well.
You need his.
Okay, anybody else?
Oh, I
All
think
right,
we're
we'll
good.
start counting.
All right, perfect. Thank you. Oh, already. Well,
That's how it happens.
I wonder who everybody voted for. Wonderful.
Hasn't joined yet.
He could throw the whole race.
Yeah.
He could. He could say, well, it's okay. Yeah. All right. So. Well, okay, Ahmed, you have to leave it open till 8 o'clock. That way Anton can. Okay, perfect. All right. Yay. There we go. So we're good. We're good. Perfect. Okay. So this is the part that Jerry always comes up and he has some wonderful little story. Hopefully he's online tonight. He's not going to talk very much. He had a wonderful trip and came back with COVID. So he is at home resting, along with recovering from some jet lag, because he went and hopped the pond and took a trip. And so he doesn't get to do the very last one of the year for a award. I lost the word. So I get to do that. So I get to have the great honor of having a person that I had not been familiar with before, sorry. But I get to give him 2 observing awards and a pin. So if I could welcome up to the stage Tom Holman for his eclipse observation. Clap, 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 clap. There we go. Thank you, thank you, thank you. So he is going to receive the Astronomical League 2024 Solar Eclipse Special Observing Award. So we have that. That's on silver level. And then also a 2024 Solar Eclipse Special Observing Award at the gold level. And I'm going to ask you to explain both of those along with a really cool pen. See, peoples, you get bling. So there you go. Thank you very much. And I'm going to grab the microphone. So you can tell us the difference between 2 and how long it took you and everything else in between.
So I'm sure a lot of you guys did the solar eclipse thing. And so the silver award is basically you have to document what you did. You have to document what the experience was. You have to have images of the start, the total, the end of the total, the end, and describe all that. And so that was pretty easy. The gold award, you have to pretend like you're an ancient Babylonian astronomer back in 700 BC and calculate something called the Saros or the Saros cycle. Are you guys familiar with the Saros cycle? So it's when I wrote notes here so I wouldn't mispronounce these things, but the synodic period and the draconic period of the moon align. And so the synodic period is how long it takes for the moon to go through its phases. The draconic period is how long it takes the moon to cross the ecliptic, going one particular direction, and one shorter than the other. But when they happened on the time of the eclipse. And then 18.04 years later, they happen again. And then, so there'll be another eclipse just like the one we saw in 18.04 years. But since that's 8 hours in the future of today, it's going to happen in Europe. So there's something like 70 something of these events that happen within their own Saros cycles that have these 70 or these 18-year periods. And so you have to actually observe the phases of the moon and observe the time it crosses the ecliptic to the best of your ability, do some very complicated math and come up with this 18.04. And apparently nobody gets it quite right except the ancient Babylonians. But that's what you get for the gold medal. And so I'm actually in the process of doing that. I'm a few months into that, but the guy that manages that program says, there, I'm going to send you the pin anyway. And when you're done, just send me the calculations. So I did the calculations based on stellarium, and they were way off. So we'll see if my observations are any closer.
Excellent. Well, congratulations.
Yeah,
Do they account for anything? Oh, I'm sorry.
yes.
Yeah, I don't know how to use these microphones. Do they account for things like the eccentricity of the orbit to give you an idea of whether it's annular versus total solar or anything like that, or?
Well, like I said, now we give it back. So yeah, there's various different ones of these similar eclipses. And so the annular eclipses will have their own cycle, and the total eclipses will have their own cycle. So there's, like I said, within this 18-year period, there's like 70 of these. So some of them are partial and some of them don't happen because they happen the wrong time of the day. But the ones that happen in the middle of the day, like we saw last April, we're going to see another one of those in 18 years, 11 days, and 8 hours from last April. And it'll be exactly like that one, but there'll be a bunch of other ones in between. Yeah. Well, the one in 18 years will be in Europe, but there's one coming up in Spain, like next year. That had one similar 18 years ago. So there's a bunch of these within a bunch of the different types of eclipses that happen in these 18-year periods.
Couldn't even stump you.
Well, thanks.
Thank you very much, Tom. Congratulations. I gave you everything back, right? Okay. Sorry, writing a little chat message. All right. And then, of course, what do we have at the end of every award, which there will be more in January when Jerry feels better. Ah, come, dang it. There it is. Get out there and observe. Should we try it one more time? 1, 2, 3. Get out there and observe. Thank you. Okay, this is the best part of my presidency, is to getting all of you to say that all at the same time. All right, now up for public service announcements. We have Michael Copper is doing Planets in the Park on December 6th at 6 o'clock to 7:30, Pershing Field Park in Minneapolis. Please go out there and bring your scopes. He usually has a big crowd and is always looking for help. Just kind of show up. The BSIG, did you want to talk about that a little bit, or should I just? Okay, Claire is going to be presenting it. Do you want to or not? Okay, where did I put the microphone? I gave it to you.
So the BSIG is online in December on Zoom,
use that.
starting at 1 o'clock, right, Suresh? 1 to 3, I will be presenting on globular clusters. The topic is why they're so cool. Talking a little bit about my own experience observing globulars and just some of what scientists know about globulars that is really awesome.
Excellent. Thank you very much. And that's on Zoom.
On Zoom on Saturday
On
at 1
Saturday.
o'clock.
Yep. All right. Perfect. And then we have the LLCC. Hate to disappoint.
Oh,
Yeah.
okay. So I was going to bake astronomy cookies for Northern Nights Star Festival this past August. And then unfortunately I wasn't able to attend. I had to go to a funeral and I missed the whole event. But I made the cookies later. And astronomy cookies, but including a beaver and a porcupine because they were Long Lake related. And then when I found out from Chris that dill prickles passed away, I sent the picture to Trina so she could include it.
Yep. Yep. And I love that. The little Photoshop of the dill prickles, rest in peace. That's wonderful. Did you grab a ballot, sir? All right. Okay. And then
Now,
CTO.
for anyone who doesn't know, Dill Prickles
Oh,
was a resident porcupine at LLC. And
yeah.
I don't know how many years, a
A
lot.
lot. Yeah, he was not afraid of people. He would just wander around right next to you and kind of do his thing and drag, birch branches. Oh, the beaver was doing the birch branches? Okay, okay. Yeah, that's right. Porcupine. Yeah, dill prickles, yes. Okay. It's a bad pun. Anyhow, CGO is, the committee itself is still looking for a couple more members. Just reach out to the CGO at CGO email address and say you're interested, or post in Slack, because we're just looking for a few, because I am leaving the committee. I'm not leaving CGO. I'm just leaving the committee and handing it off and doing some other things. And so they need some people. So please volunteer. The whole club is based on volunteers. And then we also have a matching funds for December, and that includes donations, renewals, new memberships, anything, just regular, here's a gift kind of deal. Not sure if it's like, if we're in a estate, if that gets a match, but probably not. But that is an option for anybody who's doing end of life things, to give your passion after your death as well. We've had a few of those. So just keep that in mind. So if you haven't done it, renew early, go ahead. And now, of course, this doesn't work. All right. And then I think I mentioned this last month as well. Just wanted to let you know that we have Cafe Press has our regular Cafe Press site, which I will show you in a minute how to get there, for any of the goods and services, hats, cups, totes, shirts, things like that. There's another one that has our logo and is using that. Don't buy from there, because that doesn't include any funds to go to us. So we're working with Cafe Press to get it shut down, but yeah, we're still giving it a shot. All right. And then how to get to our official Cafe Press MAS merchandise store is you go to the main homepage, go over, click on memberships, and go to MAS store, and that will bring you to the correct website. If you're on anything else and it looks strange and it's not the one that you saw in this one, whoop, not that one. On the left, where it has the MAS logo, the Minnesota Astronomical Society store, then it's not the right one. All right. Any questions, just reach out. And then we have, hopefully I've got some good time. So John, Ahmed, or whomever, where'd they go? Talking about the logos, because I'm going to give it up to you guys for that. Sure. Because I don't want to be the one talking the entire night. So anyway, we're coming up with new ones. Let John take over.
Okay, well, we have Jesse designed 3 new logos.
Well, there's actually 8.
There's actually 8.
8.
8
Yes.
new logos. And we're going to on Slack, we're going to have a voting period open. Is that's going to open up in January? Is it going to open up immediately? I don't remember if Ahmed was kind of running that, but
Yeah, he's
you'll be
about to count.
you'll be notified. And then the reason we're doing it in Slack, of course, is because only members, you have to be a member to have a Slack.
But they can
account.
email us.
And you can email as well, correct?
Yeah, you can email to the board and say, I like this one, and this one. So you're not limited to just one.
Yes.
Sorry for interrupting.
And the current logo that we have isn't going away. It's just, we're going to have the new logos as well. And then we're going to be using those as in our official letterhead or documents or available. Are there any questions about the logos as we're flipping through them here?
Yep. Why not?
Just to bring things up to date. It's just something a little bit more creative and fresh for the organization.
And I'm just going to back up for some of them. Yeah,
I guess
just
I
send us
could
some
be
picture.
open for that. Sure.
Yeah. Yeah. Right. Yeah, we put it on there and it wasn't, because it makes it odd and unbalanced. But we all know it's there. It's okay, Suresh. Well, Suresh is not voting for that one. Okay, that'll be the discussion. Feel free.
Yeah.
Yes. It will be so long. We'll take your suggestion. We'll try it out. Please write it down, put it on Slack when we get it out. Yeah. Okay. Don't worry about that one then. Just go to the other ones. But anyway, this is pretty cool. We actually have, since we don't know what the background is on the normal MAS logo, also the part of that is that we don't have the original creation of it either. I mean, whereas right now with the new logos, we actually have that original software and can upload the high-res images and create all of that stuff. The background of the black one, number 8, is the Helix Nebula. So just in case anybody was wondering what it was, that's what it is. So, and of course, these would be clear. So if you have like number 7, if you have a purple shirt, it's going to have a purple background because it's going to be thank you, transparent. Yes, you could do vintage. Yes, go to Cafe Press, get vintage before we add new ones. There we go. No, we're not, but I'll leave that to the next board. All right, so that brings me to next meeting, January 2nd, in-house. Thank you, John. In-house and online, as always. And I believe the speaker for January will be Mr. Dave Faulkner. Yes, I did not know that until earlier today, so I didn't have time to update it. So tune in. What are we talking about? What are you going to talk about? I'm sorry. Say that again.
Cosmic distance ladder.
Cosmic distance ladder. I will tune in to find out what that means because we're good. All right. And then I actually do need Ahmed because we have our next speaker. Hello. We have an update on our
It's an
election.
exercise. Okay, no, we have a total of 103 people who voted this election. That's actually a record number. And for Valts, he got 102 votes, 1 abstain. Somebody doesn't like Valts. Yep. Claire got 102 and 1 abstain. Phil got 102 and 1 abstain. Okay?
Okay,
So
the
if you're-
one abstain might have been me clearing out the poll
No,
from mine.
We already eliminated
Oh,
people who are not members who voted.
okay.
So we've had 5 members who are not members who voted online. We subtracted that. Doesn't make a difference with the result.
I
But
wonder if they
for
wanted to be in there.
for the amendment, we got 87 saying yes, 13 no's, and 4 abstains, so the amendment passes.
All right, wonderful,
it.
wonderful.
With that said, Dr.
Alright.
Bailey, it's good actually seeing you. She and I went to college together back in the
See,
day.
that's his face. That's his face now with no hair.
Well, when we're emailing, she's like, "You sound familiar. You know, you look familiar." So yeah.
Yeah,
All right,
bit a few years, but
Okay.
all
yeah,
right,
Good. Well,
So
I'll let
I
you do your
will-
talk. Thank you.
all right.
yeah,
Can
sure.
you
Oh,
see our room at all?
yeah, I think once let me see what happens when I share
If
my
you
screen,
want
if
to
I can
see,
figure out how
otherwise I
to,
will just
um,
block the camera. Up
Yeah.
to you.
I think, let's see, once I go into slideshow mode, it's sort of hard for me to see videos.
I will turn off my camera and you
yeah.
are going to do your thing.
Okay, but yeah, very much welcome questions, interruptions. So this can be interactive. And yeah, I really much appreciate the invitation to speak to y'all. As Ahmed mentioned, we're both undergrads at the University of Minnesota in Twin Cities around the same time. We're a few years older now.
Let me
Um,
get to the other
Oh,
mode.
sorry, is somebody asking a question? Oh, okay. And yeah, so it's nice to be talking to my Minnesota kin once again. Yeah, I did my undergrad at the University of Minnesota in Twin Cities, and then did a graduate program in Tucson, Arizona. Had a couple jobs around California. And now I'm at NASA's Jet Propulsion Lab in Pasadena, in the greater LA area. Should give my usual disclaimer as a government employee. These opinions are my own and not those of NASA, but opinions of an exoplanet astronomer. And I today I kind of want to talk to you a bit about some of the different ways that astronomers find exoplanets. Some of you may know this already, so bear with me. And then towards the end, dive in to a little bit more detail about the method that I use and the instruments that I work with, and hopefully leave some time for questions at the end. But if there's questions that come up in the middle, feel free to let me know and we can chat. I always like to set the scene of an exoplanet talk by reminding us that most of us here in this room were probably alive at a time before we knew about a single planet orbiting another star, and these exoplanets were entirely science fiction. Certainly the case for me, and it's really amazing to think about the progress that we've been able to make in these last 30, 40 years from pure science fiction to knowing about literally thousands of planets. With the first exoplanet that was discovered in the 1990s, because of the biases in detection of the types of planets that are the easiest to detect, the first one that astronomers found was the size of Jupiter, but in an orbital period around its star that was only a couple days. So it was a baking hot super Jupiter, already something that was completely unpredicted by our model of how solar systems form and evolve over time. And that's been kind of a theme throughout as astronomers have discovered more and more planets. We've challenged and updated and challenged and updated our theories of how planetary systems form. And today, we know of more than 5,000, close to 6,000 confirmed exoplanets, many more candidates that we still need to confirm. And from that number of detections and our understanding of how sensitive we ought to be to planets around different stars, just because of the limits of our detection capabilities, we can infer that basically almost all stars have at some point in their lifetime have planets. So when you look up at the night sky, it's not just a night sky full of stars, it's a night sky full of planets, which I just find astounding, right? And as somebody who studies exoplanets, my questions, are in their biggest form are solar systems like ours common, or are they rare? Are Earth-like planets common or rare? And especially, do any of those exoplanets host life? Obviously, we don't know the answers to all of these yet, but we're learning, and we're learning some really interesting things along the way. And that's kind of what I want to talk to you about today is some of the interesting things that we've discovered on the path to answering these questions. So there we go. All of you know the architecture of our own planetary system, with the terrestrial planets closest to the star and the gas giants and ice giants farther away. And we had built up this beautiful formation model of how our initial cloud of gas and dust condenses and forms planetary systems in this architecture that ought to always produce rocky planets on the inside, gas planets on the outside. And then, as I mentioned before, the first planet we found totally broke that. As we've improved our formation theories, we've been able to come up with ways to make planets migrate closer to their stars over time through interactions with other planets, maybe clearing out all of those terrestrial planets in between. So there's one type of planet that's totally unlike anything we have in our own solar system. We found brown dwarfs imaged them, in fact. And of course, this is just an artist rendition because we don't have the high spatial resolution to take a map, but we've seen them as points in the sky. That these brown dwarfs are somewhere in between, a planetary mass thing and a star. They're big enough to burn deuterium in their core, but they're not massive enough to get hot enough to burn hydrogen, and that's what would make the transition to a low mass star. So we've no brown dwarfs in our own system, but they're not uncommon in the universe. And in fact, what we're learning is probably the most common type of planet, at least in the inner parts of planetary systems where we're most sensitive to today. The most common type of planet is something we also don't have an analog for in our own solar system. It's super Earths. So it's larger in radius and mass than Earth, smaller than Neptune. And one of the big outstanding questions in exoplanet science right now is, are these super Earths, scaled up rocky planets, or are they mini Neptunes, scaled down gaseous planets? Because you could imagine you'd have very, one of those would be much more hostile to the formation of life than the other. And so if we can better understand the properties of these super Earths and mini Neptunes and find ways to distinguish between them, we'll have a much better grasp on how common Earth-like planets, or at least super Earth-like planets, might be within the universe. So that's been another really fun discovery along the way. But all of these planets, all of these thousands of planets that we've discovered to date, the vast majority of them, if you look at, this is a histogram of the number of planets as a function of the separation from their star, with Mercury, Earth, and Mars shown here. The vast majority of planets are incredibly close to their stars, and that we've discovered and confirmed. And the vast majority of planets that we've detected so far are far larger than Earth and are not rocky. And so, given these two things, you might ask yourself, well, okay, does that mean that rocky planets more than, orbiting more distantly than Mercury are just uncommon? And should we be really worried about the fact that could mean that there are no Earth-like planets anywhere in the galaxy? And luckily the answer is no, right? We have biases in what we can detect, and I'll kind of walk through that with a couple of the different detection methods. And then, as I said, we haven't gotten to the point where we can detect life on other planets yet, and haven't gotten to the point where we've detected something that's truly Earth-like, but we're on the path, and this, I think it's possible within my lifetime. And that's kind of where I'll end the story today. So talking about the different methods for detecting exoplanets, you may have heard about the transit method, the Kepler mission or the TESS mission. You can, and we'll go through these in more detail, but you can see the shadow of an exoplanet when it passes in front of its star. You can indirectly detect an exoplanet by noticing the wobble of the star, movement of a star as a planet tugs on it while it orbits. We can also detect exoplanets using general relativity, because a massive planet will in fact bend light from background stars around itself to make it in a way that we can detect. And you can also literally take pictures of exoplanets, and that's what that's my area of specialty. So I'll probably give that one a little more attention towards the end than the others. But I think it's interesting to hear a little bit about each one of them. And the important thing to know is that the transit method and the radial velocity method are best at detecting planets that are close to their stars, whereas the microlensing method and the imaging method are best at detecting planets farther from their stars. And it turns out those first two methods, the transit and radial velocity, are the most prolific because you can do huge surveys. And so we'll talk about each one. So the transit method, I love this picture of Venus. I'm not sure if you can see my mouse here, but that little dot suspended next to the McMath Solar Telescope on the ridge of Kitt Peak is Venus transiting in front of the sun at sunset in Tucson. And we of course can resolve the disk of the sun, and we can resolve Venus in this image. But if you imagine as an astronomer observing this system from many light years away, all you can get is the integrated light observed from the star. But if you track that with time, when the exoplanet's passing in front of the star, of course it blocks some of the light. The amount of light that it blocks is proportional to the ratio of their two areas. So from the transit method, you can recover how large the planet is in radius relative to the radius of its star. And we use models of stars to give us a model predicted radius. In most cases, we say, oh, a star of the temperature of the sun is going to be roughly the size of the sun. The cooler stars we know are smaller than the sun, and we use those model predicted radii then to predict, given that ratio, what is the size of the planet that just transited. Mm-hmm. Oh, was there a question? Oh, okay. And we also, because say a sunspot rotating into the disk or a flare can impact the brightness of the star as well, we usually require say 2 or 3 observed transits to consider an exoplanet confirmed, or at least a high quality candidate, which means you have to observe a planet orbiting that star at least 3 times to be confident that it's real. And we know from Kepler's laws that the period and the semi-major axis are related by period squared is proportional to semi-axis cubed. In other words, the farther the planet is from the star, the longer its year is. And that means if you wanted to detect something like our own Jupiter, which has a 5-year period with the transit method, you'd have to be observing for 15 years, and you would have to observe that star during Jupiter's transit. And so it gets increasingly unlikely as you get to larger and larger and larger orbital distances that you would be able to detect a planet this way. It's really good at finding planets close to the star. But we can survey huge chunks of the sky and monitor the brightness of hundreds of thousands of stars at a time for for over several Earth years. So that means we have a really excellent census of planets that are orbiting on periods much shorter than an Earth year. So that explains the big bump in the histogram that I was showing before. This is an all-sky image, almost all-sky image, put together from images from the TESS mission, which surveys the sky in strips of about 1 month per field and observes literally hundreds of thousands of stars to look for these transit effects, and has discovered thousands of planets and thousands of candidates at this point. And if you consider it turns out that most planets that are known to date have been discovered by this transit method because you can so easily detect them with all sky surveys. And in fact, one of the really neat things about the transit method is that it's very amenable to amateur astronomers contributing scientifically. Yes, the planets that are orbiting around the faintest stars do require larger telescopes to collect enough light to be able to detect them, but planets that orbit around bright stars, you don't need a huge telescope to be able to get the precision in your photometry to detect that dip from the exoplanet. And there's this really wonderful program spun up by my colleague Rob Zellum, who was at JPL but is now at Goddard Space Flight Center, called Exoplanet Watch, where they welcome the contributions of community members all over the world who have what you need is a telescope and a camera, and a CCD camera. And then they provide software that can help you process that and observe the transits. And this is important scientifically because when you first detect a planet with the transit method, you don't measure its period with 100% accuracy. You have a little uncertainty on how long its year is. And if it's been a while since you last observed one transit, you're gonna have some uncertainty on when the next one occurs. And if you want to observe that planet with an observatory like the James Webb Space Telescope, where time is incredibly precious, you don't want to have to sit there and say, well, maybe the planet is going to transit sometime in this 1 day window. We're not quite sure when, so we're going to point James Webb at it for a whole day. Like that's a waste. Let's use these smaller facilities to refine the periods, refine the times that we know the planet will transit so that we can efficiently use our space telescope time. And I know Rob has told me that he's collaborated with folks in the broader amateur astronomy community. They end up on scientific papers, so I really encourage you to check this out. And it's a great program. And so method 2 is the radial velocity method. This is the one I alluded to with the wobbling star. The data that you analyze is a very high resolution spectrum. This is a high resolution spectrum of a sun-like star taken with the Keck Observatory. And the way that this method works is by observing the starlight over a period of time and watching for a Doppler shift as the star moves towards and away from you as the planet orbits, because the planet and star orbit a common center of mass, which means the star actually does appreciably move around that common center of mass over time. For small planets, it's a small tug. It's not a very fast motion. It may only be 10 centimeters a second or a meter per second. It's not a very fast motion, but with a high enough precision spectrograph, you can measure a Doppler shift of only a meter a second of the star, a walking speed. And again, this method is best at detecting big planets that would have a stronger pull on their star. And it's a little bit more sensitive to longer period planets because we don't usually require observing multiple periods because there are fewer false positives, fewer things that could masquerade as an RV planet. So that allows us to detect planets that are somewhat farther from their stars. But, we're getting out to kind of Jupiter distance now with some sensitivity, but still not much beyond that. And only Jupiter mass things out at those wide distances. And I think in the interest of time, I'll skip over the details of this gravitational lensing, microlensing method for detecting planets, but we can always come back to it in the Q&A if there's time and if there's interest. But this is a method that has not historically been used very much because we didn't have large survey telescopes capable of detecting it, but we will in the late 2020s have an observatory that will conduct a huge survey using this method, and I expect we'll find thousands of planets. So we have those two indirect methods that I've talked to you about for finding planets. You can indirectly measure a planet's size. You can indirectly measure a planet's mass. Size and mass, you both know that, they all know that equals density. Is that sufficient? Is that all we need to know about the planet? Well, yeah, from that you can tell if it's a gas giant or a rocky planet, but you don't know about its temperature until you think about the fact that the orbital period gives you the distance from the star. So you can calculate its equilibrium temperature. You can tell whether it might be in the zone where water could be liquid on its surface, the habitable zone. Okay, so now we know a density. We could say, yeah, that's a rocky planet. Yeah, that's a rocky planet in the habitable zone. How confident are we that that's Earth-like? And you only have to look at our own solar system to say, well, boy, that's really not enough, right? If you compare Earth and Venus, both of them are in our sun's habitable zone, where liquid water could be on its surface. They have similar radius, they have similar mass, they have similar density, but Venus's atmosphere is so different than Earth's. It's so rich in carbon dioxide that it has this runaway greenhouse effect. But if it had an atmosphere more like Earth's, it could potentially be habitable. So you can't tell just from mass, just from density, or just from location. And only one of these things. In Minnesota, only one of these things can have the boundary waters. I had a lot of good canoe trips up there. LA does not have anything like the boundary waters, and I do miss that sometimes. And so what we should do is to tell if a planet could be habitable, or at least to learn more about its properties, whether it's rocky or gaseous or icy, is to observe its atmosphere. And to try to uncover the constituent molecules that make up its atmosphere. And we do that with a spectroscopy. So meaning, splitting the incoming light into its component colors. We can do this in optical wavelengths or infrared wavelengths, depending on what compounds we're looking for in the atmosphere. This is just a sort of a generic cartoon of a planet that has some combination of water and methane and carbon dioxide in its atmosphere. And luckily, well, I guess I can show in this cartoon, one easy way to do that, right, is to use the star as a backlight for the planet. In the cartoon at the top here, you can see that the starlight is shining through the atmosphere of the planet as the planet transits the star. So-called transit spectroscopy is a way that for at least the brightest stars and the biggest planets with the thickest atmospheres, we can study the atmospheres of transiting exoplanets. And what kinds of stars and what kinds of planets are amenable to that? Well, you only get a transit once every year of that planet. So you want to observe exoplanets that have very short years, very short periods, so that you have multiple opportunities to take that spectrum. So you can take the spectrum and over time build up a signal to get more and more sensitive. But of course, the hotter the star is, the farther away the habitable zone is from that star, so the longer the period would be. And that means we really, with this method, are not able to access planets in the habitable zones around sun-like stars or hotter stars, right? Think for our own Earth would only transit once every Earth year. And if you need 10 or 20 or 100 transits to build up enough signal, you're spending a lifetime just collecting enough data for one planet. So instead, transit spectroscopy is really good at studying the atmospheres of planets around cool stars, right, where their habitable zones are so close that you might have periods that are measured in weeks or months instead of years. And in fact, the James Webb Space Telescope has been doing this for the last several years, and has detected really interesting molecules in the atmospheres of these short period transiting planets. But I want to caution, because I think probably we're a little bit guilty of this in astronomy, that everybody wants a press release, everybody wants a headline, and the magazines want to sell. So you probably have seen how many times, right? Astronomers find planet in habitable zone with water, and you're probably asking yourself, like, okay, we found that before. So does that mean we found life? How do I know if this is interesting or not? What does that mean? And I think it's kind of important to contextualize this by saying, the kinds of planets that we can do transmission spectroscopy for right now are super Earths, a few super Earths, and Neptune and above. And you not only have to care about whether you've found water in the atmosphere of a planet that exists in the habitable zone, but you also have to care what its atmosphere looks like. Remember, think back to how Venus's atmosphere makes it uninhabitable, even though it's in the habitable zone. Well, okay, that same planet where there was the first detection of water in a habitable zone planet, actually, there's a lot of methane too, right? And then that probably tells you, well, okay, that's what's not shown in that headlines. There's also hydrogen. There's also carbon dioxide. So it's not an Earth-like atmosphere. So just worth pointing out that even though you've probably heard about water vapor on a planet in a habitable zone, it doesn't mean that we found a terrestrial planet with oceans. And certainly it doesn't mean that we found any evidence of life yet. But it's still really interesting. We're still getting to learn a lot about the types of exoplanets that are out there, learn about their chemistry. But sometimes it can get lost in the headlines, that nuance. And the other thing about these planets that are orbiting these low mass cool stars where the habitable zones are very small, so these transiting exoplanets, they are bombarded with stellar flares. It turns out that these low mass cool stars are way more active than our own sun. They throw out mega flares that are far larger and far more frequent than what our own sun expels. And these planets are much closer to their star than we are to our sun. There's a big question in astrobiology. Could life survive in the presence of these mega flares? That's an active topic of research. How damaging would those be? And then the other confounding factor is that these cool star habitable zone planets are so close to their stars that they get tidally locked, just like the moon does to our sun, or to our Earth. So the same side of the moon always faces us in its orbit. The same thing happens to these exoplanets around cool stars. The same side of the planet is always facing the star. And what we think that means is that for a terrestrial planet, you would have one side that's really quite warm, maybe too warm for there to be liquid water. Maybe it would get desiccated and be a massive desert. The dark side becomes incredibly cold. It would just be an icy world. So then, maybe does that mean if there is liquid water, it's only in the dawn and dusk regions of this planet? And then it's bombarded with flares. And boy, I mean, all of these confounding factors mean that we're not sure, for a lot of reasons, how likely it is that life could evolve on a terrestrial planet around one of these very cool stars. And that pushes us to try to discover Earth analogs around stars more like our own sun, where we understand a little bit better what life could look like, and it seems to be a little less hostile. And that's going over time to push us towards this technique called direct imaging, which is literally taking pictures of planets. This is a time-lapse video of actual images of 4 super Jupiters orbiting around the star HR 8799. The star would be in the center of this image here. It's been blocked out both optically in the camera in ways that I'll talk about in a minute, and also in image processing afterwards to further remove the starlight glare to see these planets. In this video, so what we can do today from the ground with telescopes like Keck or the Very Large Telescope or the Hubble Space Telescope or the James Webb Space Telescope are super Jupiters, things that are several times more massive than our own Jupiter and that are very young and still hot and glowing in the infrared from the heat of their formation. We think that our own Jupiter and many of these massive planets start out several thousand degrees Celsius. And that's enough that you can be relatively bright in the infrared and easier to detect, certainly, than detecting in reflected light. And the other thing to notice, if you look at this little scale bar at the bottom here, that bar is 20 astronomical units, or 20 times the Earth-Sun distance. For this system, that means we are seeing planets that are at least as far as Neptune and some farther than Pluto. Again, breaking our solar system formation theories, or the theory we came up with to explain our own does not explain these. And this is the detection bias of direct imaging, is we're more sensitive to brighter planets, and we're more sensitive to planets that are farther from their stars. This star's habitable zone would be really completely unreachable, at least in this image, and with the technology we have today. Where we're going, and what I'll talk about for the next few minutes, is kind of the arc towards being able to reach habitable zone terrestrial planets and take images of them within the next couple decades. So to put this slightly more quantitatively, the things that we can image with today's telescopes, these young, hot, self-luminous super Jupiters, are about 1 million times fainter than their stars. And that actually works out to about a firefly in a lighthouse. But now put that firefly and lighthouse halfway across the country, right? You're looking at stars, you're looking at systems that are many light years away. So even that image that I showed you of these planets orbiting at a Neptune or Pluto distance, we have to have such high resolution that it's like we were looking at a firefly next to a lighthouse 20 feet away, halfway across the country. And for those of you who love graphs, I'll make this even more quantitative. The things that we measure are how far apart is our planet from its star in the image in units of arc seconds. So 1 arc second is 1/3600th of a degree. And a degree is roughly your pinky held out at arm's length. So slice that into 3600 bits, and that's 1 on this graph. And the y-axis is the brightness ratio between the planet or a detection limit and its host star. Each one of these squares are the kinds of super Jupiters we can see now, about 10 to the 5, 100,000, 10 to the 6, a million times fainter than their stars at separations of around an arc second. And then detection limits from different telescopes I'm showing here. Blue ones are visible light telescopes and red ones are infrared telescopes. And where we want to go in the long term, of course, is to detect things like our own solar system. So a Jupiter around a sun-like star, Earth around a sun-like star, even if that sun-like star is in our nearest neighborhood of 10 parsecs, we're still talking about improving our spatial resolution, being able to look 10 times closer to the star than we usually look today, and going 4 orders of magnitude deeper. It's a pretty tall order. So we have a few stages of instrument development. And I'll talk first about the technologies that we use to help suppress the starlight to allow us to see things that are so much fainter than their stars. And this gets back a little bit to the theme of eclipses. Is the technology that we use is called a coronagraph. Not because we use this to observe the sun now, but because historically this kind of technology was first invented to artificially block our own sun's light to observe the corona. So all of us who are lucky enough to have observed a total eclipse in real life have observed a natural coronagraph. And now we try to emulate that within our telescope system to create artificial eclipses of other stars so that we can reveal the faint exoplanets around them. And this little video is going to walk through the various components of a coronagraph system. So we'll start out by seeing the light from the star plus planet coming into our telescope. This potato chipping is meant to kind of show that the light has been distorted just a little bit as it came in by imperfections in the telescope, small polishing errors, little bits of thermal distortions as the telescope heats or cools. Anyone who's brought their telescope outside to view on a cold night from a warm house knows you have to adjust the focus as the telescope thermalizes. So this is a small version of that takes place all the time, even after a telescope, space telescope has been orbiting for many months. We'll see the light come into the system. We have our science camera image here. We're adding that coronagraph right in front of the star. We're at the focus of the image. We put an opaque spot right underneath the star, and it removes some of the starlight. It removes the starlight right where you put the mask, but it doesn't do much for the glare. We have to add a separate pupil plane, so-called Leo stop, named after the inventor of a coronagraph, Bernard Leo. That's a second piece of optics that further blocks the starlight. And this blue light here is showing you a planet that's coming in just a little bit off axis, just a little bit different location in the sky, bypasses that opaque mask and gets transmitted over to our science camera. Now we've suppressed the starlight so much that in the short exposures we can no longer see it. And then we'll crank up the exposure time. Oops, oh, darn, sorry about that. We'll crank up the exposure time and we'll see that there is still quite a bit of residual starlight glare left in the system. That's because of those optical imperfections. And so we'll measure from that image what we think the optical imperfections are. We'll send a counter command to an actual deformable mirror, a mirror that can bend and flex it with precision of nanometers or picometers to perfectly compensate for the optical errors in the system to further suppress the starlight until you can finally see the planets in orbit. At least, that's how it works in theory, and even in practice. This is how astronomers have been able, with ground-based telescopes like Keck, to view exoplanets because the atmosphere blurs the star image and causes a lot of glare, but we can use an adaptive optic system and a deformable mirror to counteract for some of that smearing to view these super Jupiters on ground-based telescopes. And going to space, where we want to try to get to planets that are maybe 100 million or 1 billion times fainter than their stars. That's more than we can achieve on the ground. But we still are dealing with small optical imperfections and polishing and thermal changes and warps in the system, even in space. So we still need this adaptive optics and deformable mirror technology. It's just applied very slowly and very precisely. The project that I work on is the coronagraph instrument on the Nancy Grace Roman Space Telescope, which is going to launch less than 2 years from now if all goes well. And we hope, if it performs as well as we expect, we think we may get the first visible light image of the light reflected off the cloud tops of a true Jupiter twin around a sun-like star. The Roman telescope is not named after Rome, but after Nancy Grace Roman, who was in fact actually the first chief astronomer of NASA. When NASA established its astrophysics division in the late 50s, she was its first chief. She was the champion of space astronomy, earned the moniker the mother of Hubble. It was her vision to understand what you can achieve in space by sending telescopes to space. And even looking back to just a very short little letter to the editor she wrote in 1959, positing that, well, if you had a space telescope above the blurring effects of Earth's atmosphere, you ought to be able to image planets around nearby stars. So it feels really appropriate that our exoplanet imaging instrument is on a telescope named after Dr. Roman. And the technology we have in our telescope is, an advanced version of what I showed in that cartoon movie. We have a couple different types of deformable mirrors to compensate and reach better than 10 picometers, so 10 to the minus 11 meters average error across the surface of our mirror after correction. That exquisitely focuses the light onto these different types of coronagraph masks to block the star's light and suppress it by a factor of about 100 million. Now, we've suppressed the star's light by 100 million, and the planets are incredibly faint next to it. We're actually literally receiving 1 photon per pixel from the planet every few seconds or even every minute. So every single photon that we receive is precious. So we have a type of new CCD technology called an electron multiplying CCD that is able to detect individual photons as they arrive. And then we have some data processing steps afterwards to remove as much as we can of the residual starlight to uncover the planets. These are, of course, simulations since we haven't launched yet, but my hope is we'll look something like that in a couple of years. And the types of technologies I've got here in blue are ones that have flown on other space telescopes before. Hubble and James Webb both have coronagraph masks and have used advanced image processing to further improve the sensitivity. But no space-based telescope has ever used a deformable mirror like this for a coronagraph to improve our sensitivity. And no space telescope or ground-based telescope that I'm aware of is using electron multiplying CCDs in this very sensitive photon counting science application. So the coronagraph instrument on Roman is really our purpose is to be a technology demonstrator. Since so many of these things have never been done before in space, have never been done to this precision, our job is primarily as a tech demo, but we're going to look at interesting things while we're up there. And it's real, it's built. Here's an image of our optical bench. with our deformable mirrors and our photon counting detectors, and then a number of different masks and optics to move the light between those different coronagraph mask planes. We built almost all, a vast majority of the components at JPL, and we did the testing at JPL. Here, the instrument's being ready to go into the vacuum chamber for its run for the record performance testing. The optical bench now is wrapped here in Mylar. All of the electronics that run the deformable mirrors and the cameras and everything else are here below it. Heat and is an enemy in these cases. So we have radiators that will serve to cool the electronics by facing space and offloading the heat that the instrument's generating. And then just for this test, in the vacuum chamber, we have a telescope simulator that will inject a fake star image that looks like we expect to receive from the telescope itself. And here's a little time-lapse video of that process that we saw in the movie, the cartoon, where we'll take a science image. We see there's still a lot of starlight glare, and we'll measure that glare, to calculate a deformable mirror command, send that command, and you should knock down the glare a little, knock down the glare a little, and knock down the glare a little. So that you'll see kind of an iterative process of suppressing the starlight glare as we move our deformable mirror. So we start out with a detection limit of maybe only 10,000 times fainter than the star. And by the end of these iterations, we'll be at a detection limit of more than 10 million times fainter than the star. And because these are just tests in our vacuum chamber, we don't have a planet simulator, so there's no planet to show, but this is actual real test data with a simulated star. And now the instrument's complete, and it's been delivered to the Goddard Space Flight Center to be integrated with the rest of the telescope. I don't have the most recent picture here, but I hear earlier this week our telescope was actually installed in the main instrument carrier, and the primary mirror and secondary mirror were installed on top. So it's really coming together. And with Roman, we'll observe these hot, young, self-luminous super Jupiters, and hopefully take the first visible light images in reflected light of true Jupiter analogs. And one of the things we'll be able to tell based on their visible light color is whether they're mostly cloudy, like Jupiter, or have more clear atmospheres like Neptune or Uranus. And then moving forward, right, in NASA's long-term arc towards the pale blue dot around another star is the Habitable Worlds Observatory. It's going to use all of these same flavors of technology. It's going to use coronagraph masks. It's going to use deformable mirrors. It's going to use exquisitely low noise sensitive detectors, but a much larger telescope mirror, maybe 6 meters instead of 2 meters, for more light collecting power, to be able to directly image and take a spectrum of a true Earth twin around a sun-like star. Right now, the Habitable Worlds Observatory is just at the concept stage, but we're imagining that it could come together in the early 2040s, perhaps. The technology development for it is going on right now. We're at the stage where we have to prove that we can make next generation detectors and deformable mirrors and coronagraph masks that would meet the really stringent requirements that this concept needs. That technology maturation is going to happen over the next 5 to 10 years. And we hope that we'll get to the point where NASA would approve this as a full mission, so that within my lifetime and yours, we could take that pale blue dot image of an exoplanet around another star. And that's all I had to say, and I'm happy to take questions. Hopefully folks hear me. I didn't just talk into the void. So how do you usually do this? Should I stop sharing screen and look at the chat? Let me try that. Because I'm not hearing any audio, so I'm just going to look at the chat. I could not tell you why the northwest angle is not shown in the logos.
I'm stuck.
Oh, I hear you now.
Do you hear me now?
How
Okay.
about- Can you hear me?
Yes. Yes.
Oh, great. So this is great. I love this talk. This is awesome. It's only been what, 30 years since the first exoplanet was discovered. I think
Yeah.
51 Pegasi was like 1995.
Yeah.
So,
Yeah.
with all the new technologies coming online, the new observatories, I snuck a peek online and it looks like there's other ones coming too. The European Plato mission, the aerial mission.
Mm-hmm.
My question to you is, using a crystal ball, 20, 30 years from now, what are we going to know that we don't know now? What do you think we're headed?
Yeah. So Plato and Roman, or Plato and Ariel, are going to give us a more complete census of those interplanetary systems around cooler stars. One of the biggest questions that we still have is how common are Earth-sized planets around all types of stars, but cool stars included. And of those, how many might have atmospheres that are somewhat Earth-like versus other types of exoplanets? Plato is another one of these discovery missions that will discover a number of transiting exoplanets. And then Ariel is a mission that's dedicated to spectroscopy of their atmospheres and ought to increase dramatically the number of planets whose atmospheres we know a lot more about around these cooler stars. The mission that I mentioned in passing, the microlensing mission, that is actually the other instrument on board than the Roman Space Telescope, will take a census of this region of parameter space that we just don't have access to right now, which is planets that are kind of Earth-sized in Earth-like orbits around sun-like stars out to sort of Jupiter. Right now, transits and radial velocity are good at finding things closer to their stars or more massive, but we don't have a good census of true solar system analogs due to the limited sensitivity. Roman microlensing is going to blow that out of the water. And because right now, all that we can do in terms of projecting how common Earth-like planets are is to take the data for systems with planets that are much closer to their stars and make a projection for how common planets would be in the outer parts of those planetary systems. But the Roman microlensing data is going to give us the actual detections to understand how common Earth-sized planets are in the habitable zone of sun-like stars. That's one of the biggest uncertainties in terms of how common is life. And also one of the biggest uncertainties in the design of that habitable worlds observatory, based on the extrapolations that we have from the known exoplanets today, we think that Earth-sized planets might be around 20% of habitable zone, sun-like star habitable zones, but we don't know for sure. Yeah, and then there's JWST, there's the life concept, there's the habitable worlds concept. There's a lot of excitement building around exoplanets, both Earth-like ones and understanding that complete census of types of planetary systems.
Excellent. Thank you. Thank you. There is a couple of questions in the chat.
Yeah.
Ask the first one is that Ron Schmidt is terrestrial planet finder was canceled in 2011. Is there interferometry? Yeah.
Yes.
As an exoplanet detection method.
There are no currently funded missions right. So Ron's alluding to a different method for suppressing starlight. You can suppress the starlight to image planets either by putting an opaque occulting disk, a coronagraph, in front of the star within the camera itself, or you can use interferometry, which is interfering the star's light against itself to suppress it. And you do that with multiple telescopes, combining the light together. And if you phase them just right, you can have the starlight cancel out, but not the planet light, at least in principle. Interferometers have been used on ground-based telescopes to study dust structures around stars. They've not historically suppress the starlight enough to see planets or to see terrestrial planets. But the concept was to move to a space-based telescope, a much more stable platform, and use this technique. But it was determined that at the time the technology just wasn't there, and that's why it was canceled. We weren't sure we could make it work. But the European Space Agency, speaking of concepts, has a very early concept called the LIFE concept that would also, again, be an interferometer. And that method, I think, is probably necessary to go to the longer infrared wavelengths for various reasons. And that's a concept that's maybe like, I would guess 2050s sort of a launch timeline. So very early concept at this stage, but something a lot of people are excited about.
Okay. Excellent. And I know there's a couple of people that were here to also in the chat that were asking about the Citizen Science Project and how difficult it is to get involved. And maybe there's many ways of doing that. Is there more?
Yeah. So let me find that slide one more time so that you can grab down this guy, and let's find, does that work? Sure. Let me find the right slide here. Quite a ways back, isn't it? Let's see. But it was Exoplanet Watch. I just need to find the right slide so that I can get you. Sorry, should have maybe left presenter mode. One more. There we go. So there's the URL. They very much welcome contributions. They're really excited. The more the merrier. So there's plenty of startup instructions on their website. And that's the one I would recommend most, probably because I'm partial to Robin, and he's done a great job running it.
Okay. And is there a limit? There's somebody else was saying, is there a limit to the size of rocky worlds, and in the exoplanets that also have been photographed, have any moons been detected?
Yeah.
But
That's the question. Well, we think when we get to maybe about 10 times or 8 to 10 times the mass of Earth, you're massive enough now that you have enough gravity to hold on to hydrogen. So you end up with a more massive gas atmosphere, more like Neptune or Uranus. Below that, your gravity is too weak to hold on to the hydrogen. And in fact, when Earth was forming, it probably had a hydrogen atmosphere, and it's just lost it over time. And so exactly where that transition happens between an Earth-like atmosphere and a hydrogen-dominated atmosphere, different formation theories will give you a little bit different answer, and it will also depend on how close the planet is to its star. And let's see, the second part of that question was exomoons, right? So there's one tentative detection of a transiting planet with a moon. I would say it still has yet to be confirmed. It's kind of tentative evidence at this point. For direct imaging, we don't have the resolution to be able to see to separate a moon from a planet, but we can see planets if they're multiple planets in a system if they're several AU away from each other. But we couldn't resolve our own Earth Moon system.
okay. Was there any other in-house, John? By the way, Matt, can you mute? You're not muted. I think it's picking you up.
Information on the massive planets?
Oh, I only caught the end of that. Could you repeat the question?
Oh, sorry. Is it possible to tell the massive planets from direct imaging?
Yeah, you guys are good at finding the weaknesses. Not directly. It's model dependent. So far. So these self-luminous planets, we have models of planet formation that will predict how a planet cools over time. A planet of a given mass will cool over time, depending on how it formed. There are, and we can know the age of the planet by age dating its star. So you know, you might say, well, this star is 10 million plus or minus 3 million years old. And so you can get a mass, you know, say, yeah, maybe that's 10 Jupiter masses plus or minus 3. With the caveat that there are multiple planet formation models, and depending on whether the planet just sort of collapses out of its disk altogether at once, we call that gravitational instability. That starts up very hot. Or it could grow more slowly over time. It could grow up from a core, you know, and we talked about how if a rocky planet becomes massive enough, it starts to hold on to a hydrogen atmosphere. So you could grow up a rocky core and then hold on an atmosphere. That's cooler because it's a slower process. So depending on whether you think it formed by so-called core accretion or by gravitational instability, you'll have a different starting temperature. So you have to make an assumption about how it formed. Now, the exception in the future, we'll be able to use radial velocity to observe the same planets as we're directly imaging. The Roman Space Telescope is going to be the first one that we think can do that because radial velocity has gotten better and better. Imaging will be more and more sensitive. And finally, for just a couple planets, we'll be able to have both a radial velocity measurement to measure its mass and an image at the same time. And that's going to be the ground truth.
Interesting. Thank you very much. Let's see, we have a couple more questions online here
Yeah.
as well. One of them is from Kirk. Do we have the data? Do we have data to confirm tidal locking of planets around cool stars, or is that theoretical?
Yeah, we do. So I mean, I'll caveat this with saying this is not my area of research, but what you can do for planets on these very short periods is you can look at the overall total light from the system over the planet's entire period. Not just when the planet's passing in front of the star and looking for the dip, but actually the planets that are the very closest to their stars get quite hot and start to emit their own infrared light. So if you look at the infrared brightness of the system over time, as the planet goes around the star, you can actually see that there's a hot side and a cold side to these planets, which we think is evidence of tidal locking.
Okay. Let's see what else. Another person would like you to come back and provide updates on Roman after it launches and begins its mission.
Lovely. I hope I'll have something good to share.
Yep, exactly. A lot of thank yous. And then Ron asks a follow-up question.
Yeah.
During 30 years of exoplanet detection, what did we get wrong?
Oh, what did we get wrong? Well, I mean, the planetary formation theories have had to be updated so many times, right? You have to form hot Jupiters, you have to, very close to their stars, you have to form super Jupiters really far from their stars, you have to mostly form super Earths in terrestrial zones. Like all of these things were definitely not what we had predicted from our original own solar system formation models. There's also been some false positives, right? If you have a binary star system where the stars, one just barely grazes in front of the other. Say you have one hot star and one cool star. So the cool star is dimmer and it blocks just a little bit of the brighter star's light. That looks kind of like a transit, right? I mean, it is a transit. So you can mistake those for exoplanets if you're not careful. And one of the ways that you can distinguish those two things is by following up the system afterwards with radial velocity. And if your radial velocity shows a whomping signal, then you know it's something massive around it. So there have been false positives like that. In direct imaging, you can be confused between a planet orbiting the star or a background star if you don't look at it over multiple years. Because a background star will stay in the same place, but the host star will move slowly in the galaxy with a motion that we know we can measure. So a background star should move slowly away from the host star, whereas a planet should move together. If you aren't careful about that, there have been a couple of cases where people said, oh yeah, I've discovered a new planet, and in fact, it was just a background star. So there are lots of false positives you have to be careful of.
Excellent, excellent. Are there any other questions that we have? Hold on, Conrad. Or sorry, Gunnar. I was seeing Conrad. It's right in front of Render. No.
Oh, okay. So I'm reading now about how they're going to be put through, or the telescope's going to be put through thermal vacuum
Mhm.
testing.
Mhm.
So you do testing on it, that's coming next, or as it gets assembled, right?
Yep. Yep.
Okay, and then just out of curiosity then, like as this develops, where will it launch? Will it launch in California or?
Ah, Kennedy.
Just kind of
Yep.
curious.
Yep. Yep. And then it, Mhm.
Anyway,
yeah, and then it'll we'll go into an L2 orbit, so at the Lagrange point that's beyond the moon, the same orbit as the James Webb Space Telescope, and you want to do that for Roman instead of low Earth orbit, like Hubble, because you need a really stable environment. You need a very stable telescope. You need one that Hubble had to go in and out of sunlight and shade every 90 minutes, so it was always flexing and creaking and groaning, and that's part of what limited its sensitivity, even though it had a coronagraph. So James Webb Space Telescope and Roman Space Telescope were out at L2, where you're always in the sun.
I'm just curious where it would launch from. Would it be California?
Oh, no, Kennedy, Florida. Yep.
Oh, gotcha. Okay.
Yep. Hopefully I'll get to go. We'll see.
I hope so too. That would be good. And then we have another question here, final one. Can you explain more on the micro lensing? Can we observe light bending in our own solar system? Can we observe other
Yeah.
planets like Mars?
Yeah, yeah. Well, thanks for humoring me. I know I planted that question. Okay, let me find. All right, let me find. I had a little movie on this. So, now I have to remember how Zoom works. All right, let's try this. So, okay. Right. So this micro lensing technique takes advantage of the fact, that general relativity predicts that massive things deform space. What we're going to see here is a background star somewhere in our galaxy. Like, let's say we look towards the galactic center. There's a lot of stars there. That star is warping its space around it a little bit. It's emitting light, and we're going to be looking for a planet not around the background star, but around a foreground star that happens to pass in front of it. Now you're going to see a foreground star with a planet that's going to pass in front of that background star from our perspective. Like, let's imagine Earth is kind of down here on the bottom of the video. And just like a glass lens that's curved can focus light to a point, when space is curved, it can focus light, or effectively it can collect light from a larger area and focus it down to one position. So if I'm sitting here as an observer and watching the brightness of the star, if there was nothing passing in front, it should be roughly constant in time. But as that lens passes in front of me, now it's focusing a lot more light towards me, and I see the brightness of the star increase. And if I look really carefully, I can see a secondary little blip here. That's the effect of this planet warping space around itself just a little bit and focusing just a little bit more light towards us. And this technique is it turns out, just mathematically, for stars like our own sun, the largest signal is produced for things that are kind of in Earth-like or Mars-like or Jupiter-like orbits. So finally, a detection method that's most sensitive to the planets that we're most excited about seeing. And in fact, we think that if you're looking at projected separation and now planet mass, this set of blue points here are prediction for all of the planets that will be discovered with the Roman Space Telescope, formerly called WFIRST, compared to Venus and Earth and Mars, and to transiting exoplanets that were known at the time. This plot's a few years old. So I'm really, really excited that, again, this is a very indirect method. The planets that we'll detect this way are hundreds or thousands of light years away, so we won't be able to follow them up, but we will know the demographics of planets in the habitable zones and farther out of sun-like stars for the first time.
Nice. Such interesting.
Mm.
Ron asked a different question.
Yeah.
Kepler stared at one field before K2, but TESS is looking everywhere. Which method has been more successful?
Yeah, I wouldn't, they're complementary, right? They both discovered thousands of planets. As you said, Kepler stared really deep at one field. I think I don't think I have a slide on that. That's okay. And because it stared very deeply at one field, for those smaller number of stars, it looked for a longer period of time, and so it could detect planets on longer orbital periods of planets more distant from their stars. And it didn't quite get out to Earth-like things around sun-like stars. It didn't quite get out to Earth's distance, but it built up a really nice census. But only for stars in that field. Most of those stars were too faint to be bright enough to backlight their planets for transmission spectroscopy. There are very few, very, very few transiting planets discovered by Kepler that can be followed up with something like the James Webb Space Telescope spectrograph. The purpose of TESS then was to survey the entire sky, only the brightest stars, so that it could discover planets around stars bright enough to follow up and do atmospheric transmission spectroscopy with things like James Webb or Ariel. So complementary, and because TESS is an all-sky survey looking, frequently repointing, it's only discovering the planets closest to the stars. So it's a different region of phase space, but ones we can study in more detail.
Wonderful. All right. Well, I don't have any more questions in-house or online. So thank you very much, Dr. Vanessa Bailey, for a wonderful presentation. And we hope you come back when you have a little bit more about the Roman Space Telescope. So
I would love to. Thanks for all the questions.
Yeah.
I love an engaged audience, so thanks.
All right. Well, for everyone else that's here, we are concluding our business meeting for the evening. And thank you so much for coming, and we'll see you in January. Have a good Christmas and a good New Year's. And for those that are here, please go over to Pizza Luce and have some after meeting dinner and celebrations. So, all right. Thank you, everybody. Good night.